Hi, everyone. Today, we're going to discuss the first monthly challenge that I posted about a month ago. The problem briefly said, given two random variables, which we built in an interesting way, find which one has the highest median. Okay, first of all, let's describe a few things. Let's do some preliminaries. So first of all, what is a random variable? So a random variable is a process which produces random numbers. But this happens according to a rule. So one way to think about it is, imagine we have a box, okay? And every time we press a button, we get a new random number. So I press the button once, I get a number. The second time, I get another number, and so on. If this random variable is Poisson, like if it follows the Poisson distribution, then every time we push the button, we only get 0 or 1 or 2, and so on. So basically, like imagine you press this button, okay? And then sometimes you get a 0, sometimes you get a 5, sometimes you get a 200 maybe. Okay. For the Poisson distribution in particular, this only gives positive integers. But still, there's some structure in this randomness. So, I mean, there's a rule, right, with which we're getting these numbers. So let's describe it. So yeah, every time we push the button, we either get 0 or 1 or 2 or 3, etc. Right? Like we never get, for example, 1.5 or -3. Okay. When we push the button, we get 0 with some probability. Similarly, we get the number 1 with some probability p of 1, and so on. We get 2 with some probability p of 2. And in general, we get k with some probability p of k. So this is basically like the structure of the randomness. It's like every time I press the button, yeah, we do get a different random number, but they do have a bit of structure. So for example, if p of 1 was equal to 1, then we always get the number 1, right? Like it's probability 1. We always get the number 1. We never get something else. If, for example, p of 0 is 1/2 and p of 2 is also 1/2, then we know that, you know, we only get 0 or we only get 2. And every time we press the button, you know, it's a 50-50 chance of which one we're going to get. This is basically what a random variable is. And this is what a random variable is in this particular case of the Poisson. So for the Poisson distribution, we only get 0, 1, 2, 3, and so on, according to these probabilities. We're going to see that with the Poisson, there is a chance of getting any number. But we're going to see together, it depends on the parameter. And that's why I mentioned in the monthly challenge that we're dealing with the Poisson with lambda equals to 2. So let's go forward with the discussion. Yeah, so like I mentioned, or actually I didn't mention this, but it must be true that p of 0 plus p of 1, like the sum of all probabilities needs to be equal to 1. You know, like 0, 1, 2, 3, and so on. They need to cover all the possibilities. Great. Now, perfect. What's a Poisson of lambda? Well, this determines specifically, this determines specifically what are the probabilities, p of 0, p of 1, and so on. They will be functions of lambda. Let's discuss it in our particular case when lambda equals to 2. If you remember, the problem said that we have a Poisson with lambda equals to 2, and then we added with a Gaussian, which we're going to discuss in a second. So let's just focus on the Poisson lambda equals to 2. When lambda equals 2, we have these specific probabilities. The probability of pressing the box or the button and getting a 0 is this constant, 1 over e squared, which we can approximate if we want to. The probability of getting a 1 is 2 times 1 over e squared. Probability of getting a 2 is the same constant, 1 over e squared times 4 over 2 factorial. By the way, this also equals to 2. But we're going to see in a second why I wrote it like this. Probability of getting a 3, the same constant, 1 over e squared times 8 over 3 factorial. And in general, the probability of getting a k when we press the button is this constant times 2 to the k over k factorial. If you're interested, you can plot this, and you're going to see that the highest probabilities are for these small numbers. This value becomes very, very low when k gets big. But as required, these probabilities do add up to 1. And it's actually a pretty cool result. You can try to think about it. It's actually quite a nice result, proving that these probabilities add up to 1. So this is a Poisson with lambda equals to 2. In general, let's see, e to the minus lambda. Yeah, so in general, it's 1 over e to the lambda. So basically for a general Poisson, lambda replaces the 2, basically. So probability of getting a value of k is 1 over e to the lambda times lambda to the k over k factorial. But, let's just focus on our particular case when lambda equals to 2. These are the values. Great. So we've determined what's a Poisson with lambda equals to 2. Now, what's a Gaussian, right? And particularly, what's a Gaussian with mean 2 and variance 2? If you remember, this is what we added, right? Like we added the Poisson lambda 2 with the Gaussian with mean 2 and variance 2. So the Gaussian is a bit different because the Gaussian box doesn't give only positive integers. It gives, like, it can give any real number. It can, yeah. So gives out any real number. So it's a bit more difficult to identify P of 0, P of 1, and so on, because now we don't have just these particular values, 0, 1, 2, 3, and so on. Any real number can appear, as a result of pressing the box. So instead, we work with something slightly different. We work with intervals. So we ask, one second. So we ask, what's the probability that the Gaussian box will give me a number in a particular interval? Okay. The probability of receiving a number in the interval 2, 3, we can call this P of 2, 3. And we can apply this for general intervals, right? Like for this open interval 1, 3, we call this P of 1, 3, and so on. In general, what's the probability that the Gaussian box would give me a number in the interval AB? We're going to call this P of AB. So the Gaussian is completely determined by these probabilities, basically. If we know these probabilities, then we can answer any questions about the Gaussian, or we can answer questions related to probabilities of particular numbers, or like a particular set or a particular interval. So for Gaussian 2, 2, we have a specific formula for any interval, P of AB. This formula is an integral that has this form. Yeah, it's not so crazy, actually, but yeah, this is what it looks like, basically. Like for any AB, it's an integral of this function. Okay, this is the Gaussian 2, 2. And of course, if you have any questions about this or about anything that I discussed previously or that I'm going to discuss, just write me a comment, and I'm very happy to answer. So this is what determines the Gaussian 2, 2. We have a formula for the probability of receiving a random number in this interval. Okay, so that's the Gaussian 2, 2. Now, what's a Gaussian 4, 4? Just as a reminder, these were the 3 random variables that we worked with. The first one was a Poisson with lambda equals to 2. The second one was a Gaussian with mean 2 and variance 2. And the third one was a Gaussian with mean 4 and variance 4. And basically, we're comparing the median of the third one with the median of combining the first and the second one. So what's a Gaussian 4, 4? It's very similar to a Gaussian 2, 2. So it's the same concept, It's determined by the probability of getting a number in any given interval AB, or in a particular interval AB. This, again, is an integral from A to B, but slightly different. So basically, this constant is slightly different, and this value is also slightly different. Yeah, these integrals look similar. There's a structure here, because the Gaussian 2, 2 and the Gaussian 4, 4 are related. We can construct both of them, and we can construct in general any Gaussian with mean mu and variance sigma square. We can construct them from a basic Gaussian, which is the Gaussian with mean 0 and variance 1. This is called the normal distribution. Okay, so how do we construct it? So basically, we get this Gaussian 2, 2 box that we can press and get random numbers. We can get it from this kind of basic Gaussian 0, 1 box. And here's what I mean by that. So to get the value of a Gaussian 2, first we get the value like we get a random number from the Gaussian 0, 1, and then we multiply by square root of 2. There's a reason why we do it with a square root, but we get a Gaussian 0, 1, or we get a normal, a random variable. We multiply it by square root of 2, and then we add 2. Similarly, for a Gaussian 4, 4, maybe you can imagine what we do. We get a Gaussian 0, 1. We multiply it by the square root of 4, which is 2, and then we add 4. Okay, so we discussed Poisson. So we discussed the Poisson, we discussed the Gaussian. We also discussed a bit how these things are characterized, right? And we saw that there's quite a difference between the Poisson and the Gaussian, because the Poisson takes kind of discrete values, 0, 1, 2, 3, and so on, and the Gaussian can take on any value basically. Okay, and then we also saw that there's some structure, and that if we know properties, or actually we didn't see this, but this is true. If we know properties of this normal distribution of this Gaussian 0, 1, then we can find the similar properties for other parameters. We're actually going to see this in the proof. Okay, now the question asks about comparing the median. So let's discuss what's the median of a random variable. And very importantly, a median is not the same as the mean. So I'm not even going to mention what the mean is. I'm just going to describe what the median is, so it's very clear for us. So the median is basically the 50th percentile of a random variable. So basically, it's the value where, with 50% probability, the box is going to give me a value less than it, and with 50% probability is going to give me a value bigger than it. That's one way to describe it kind of intuitively. We can write it with a bit of math. It's the one value a, such that the probability of getting something less than or equal to a, it's exactly 50%. And we can interpret this as 50% of the time, the random variable gives something less than or equal to a, and the other 50% of the time, it gives a value bigger than a. So it's kind of is the value that splits, the random variable in the middle. We can think about it as the middle value in a way. That's why it's called the median. Okay, there's a more technical and complete definition. This is what it is. It's the smallest value of a, such that the probability of getting something less than or equal to it, is bigger than or equal to 0.5. You can think about this for a second, and you can think sort of, where does this, where is this definition better than this definition? But this is basically the complete definition. In practice, we're going to see that it's quite clear, how we define the median. Okay, yeah, we're going to see this in a moment. Great. So we've established the preliminaries. We've established what's a random variable, what's a Poisson with lambda equals to 2, what's a Gaussian with these parameters, what's a Gaussian with these other parameters, and also what's a median. Now let's solve the problem, right? Let's see which of these two constructed random variables, which of them has the highest median. So let's go to the whiteboard. Okay, so just as a reminder, we had two random variables. The first one was a Gaussian with mean 2, with mean 4, and variance 4. Sometimes we can write this as a normal with mean 4 and variance 4. I mentioned this in the preliminaries. The Gaussian with mean 1 and with mean 0 and variance 1, it's called the normal. Sometimes people say for a general mean and variance of Gaussian, they also call it a normal. Okay. Okay, so that's A. And then B is actually a sum of two random variables. It's a Poisson with lambda equals to 2. This is a lambda plus a Gaussian with mean 2 and variance 2. Okay. One more thing. What does it mean to add two random variables? Well, if we remember the analogy with the box where we press a button and we get a number, if we want to add two random variables, then imagine, we press the Poisson box and we get a number, then we press the Gaussian box and we get a number, and then we add these two. That's the same thing as getting a random number from the sum. So that's what I mean. So basically B, like this random variable B, it's as if I want to press the box of B, I press the box for the Poisson, I press the box for the Gaussian, and then I just add them together. Okay. So the question is, which one has the highest median? Well, the wonderful thing is we know a lot about Gaussian random variables. We really know a lot. In particular, we know basically how the probabilities look like. And the probabilities look something like this. I didn't do it perfectly. I did it by hand, but wait, let me do it again. Oops. Oh, okay. Let me just try again. So it's something like this. And these are basically, it's a way of thinking about the probability of each number appearing. So one important thing is kind of, and kind of the only thing that we need to know. So first of all, something interesting, this Gaussian 4-4 is always symmetric around the mean. So this is 4. Actually, 0 is here. 0 is here. So the one important thing that we need to know about the random variable A is that it's symmetric around 4. So if X, so in general, if X is a Gaussian with mean mu, any mean mu, and any variance, sigma square, I'm putting a sigma square because the variance has to be positive. So if X is, or the variance has to be bigger than or equal to 0. But if it's 0, then there's no randomness. Like I get the same number every time. Okay. In general, if X is a Gaussian with mean mu and variance sigma square, then probability that X less than or equal to mu is the same as the probability X bigger than or equal to mu, and they equal to 1/2. We can even prove this with our description of the interval, like with, I mean to say with our description from the presentation of how we can characterize a probability distribution from the probability of it having a value between A and B. Because the probability that X is or equal to mu is the same thing as probability of X belonging to the interval minus infinity mu, if we want to be super precise, because this includes mu. And by definition, this is 1 over square root of 2 pi sigma squared times the integral from minus infinity to mu of e to the negative 1/2 sigma squared x minus mu everything squared dx. Okay, we can prove in a way that's not so difficult that this is the same as probability x bigger than or equal to mu. We can prove that it's the same as the probability of x belonging, and actually we can, let's do it like this. Now I want to use like a closed interval here. Sorry, an open interval. We can prove that it's the same as this probability, which is very similar to what we did above. I mean, it's very similar. We just changed the endpoints of the integral. So let me actually just copy this and move them here. Maybe I can make my camera a bit smaller now. maybe that's better. And put it here. Okay, good. Okay, so long story short, the Gaussian is symmetric around the mean. So the median of any Gaussian with mean mu and any variance sigma squared is just equal to mu. That's the median of any Gaussian. So we just apply it in our case. In our case, the median of a Gaussian with mean 4 and variance 4 is just 4. It's this value over here. So we have the median of the first random variable. It's just equal to the mean. It's equal to 4. And actually, we see that this variance had no role to play in the median. There is a reason why I picked this number. I'm gonna show you at the end. But this is very good. Like, we know the median of the first random variable. Now, remember the second random variable. Let's see what I called it. I called it B. Okay. Now we have B. B, which is a Poisson of 2 plus a Gaussian of 2, 2. I'm gonna call it for simplicity P plus G. Okay. And we know that P is a Poisson with lambda 2, and G is the Gaussian with mean 2 and variance 2. So basically, we just need to figure out for this B, is the mean higher than 4 or lower than 4? And then the problem is done, basically. Okay, now this becomes interesting because we're adding two things that aren't so compatible, basically. Like, the Gaussian can take on any values. Again, the symmetry over here is around the mean, which is 2. So the Gaussian can take on any values. But the Poisson can only take 0, 1, 2, 3, and so on. So it's an interesting question. How do we even find the median? Can we find an exact value? And so on. But I want to show you a cool thing. Because the problem doesn't ask to find the median. It just asks to compare the two medians. And now we actually know that the median of the first random variable is 4. So we just need to see if B has a median of 4, or, sorry, we just need to see if B has a median of bigger than 4 or less than 4. Or maybe it's exactly 4, but it's not. And we're going to see in a second. So we do something pretty cool. Check this out. Let's assume, by the way, I'm using here some terms that I haven't introduced, like, or some concepts, like, for example, this graph here, this is the probability distribution function. This is the PDF. It's the same thing as this whole function they were integrating. They were integrating over here. I haven't introduced this because it would be, I mean, how do I say this? We need these basic concepts to solve the problem. When I gave some preliminaries at the beginning, I just wanted to kind of give you kind of a brief introduction of what we're talking about here. Okay, so if we were to plot the PDF, the probability distribution function of B, let's say it looks like, we don't really know what it looks, but let's just say it looks like this. Maybe it looks like something else. We want to find the median and compare it to 4. Now, we know what characterizes the median. The median is going to be, it's going to be this value, A, where we have 50% of the probability over here, and likewise, 50% of the probability over here. This is what the median is, okay? It's always like this, and especially for like a continuous, a random variable, like we have with our B. So A is the, so the median A is the value which kind of splits the probability distribution in half. So So it's not necessarily the top, right? It's not necessarily the mean, which actually doesn't have a lot of graphical significance when we draw the when we draw the PDF. But let's do something interesting. So, okay, we want to see if this value, like we want to see how it compares to 4. Okay. Well, what if we prove something interesting? What if we prove that, what if probability that x less than or equal to 4, what if it's like 0.48, for example? Well, if the probability that x less than or equal to 4 is 0.48, then necessarily we have this cool result. Necessarily, no, let me do a different color. Maybe this one. Necessarily, we have something like this, right? If the probability that x less than or equal to 4 is less than 1/2, then 4 has to be lower than the median, right? Because basically, we need this extra 0.02 to reach 50%. So if the probability that x less than or equal to 4, sorry, x is just this, x is this random variable, right? So, you know, properly this is b. If the probability of getting something less than or equal to 4 is less than 50%, then we know that 4 less than the median. So this is good, right? And actually it's if and only if, but not for this particular value 0.48, but in general. Okay, now you can do the second part. What if instead, right? Because we don't know this probability yet. It could be bigger than 1/2, it could be less than 1/2. What's the probability that b is bigger than or equal to 4? Sorry, what if probability b big? Sorry, what if the same probability, sorry, is bigger than 1/2, is 0.6? Let's make it into a clear example. Well, if being less than or equal to 4 is 0.6, then for sure 4 is going to be somewhere here, right? Because we have 50% plus some more stuff. So in this case, median is less than 4. So this is how we're going to determine the median, okay? We're going to check the probability that our constructed random variable is less than or equal to 4, okay? And we're going to see if it's above 50% or below 50%. And that's going to tell us if the median is bigger than 4 or less than 4. Okay, hope everything is clear by this point. As always, write a comment, put a timestamp, and I will happily discuss. Okay, all right. So we've established if we want to see if our random variable has a median bigger than 4 or lower than 4, we just need to calculate this probability. What's the chance that it's less than or equal to 4? This is all we need to do, and then we place the median compared to 4. Okay, so let's do it. Let's see how we can evaluate this. So just as a reminder, once again, B is a Poisson with lambda equals to 2. This is a lambda plus a Gaussian with mean 2 and variance 2. Okay, and we wrote this as P plus G. Okay, well, let's see how we can evaluate the probability that B less than or equal to 4. The wonderful thing is, the very nice thing is that our Poisson can only take discrete values, you know? So we can evaluate this probability depending on the values of P. So, for example, in order for B to be less than or equal to 4, it's like if Poisson equals to 0, I'm going to say here, if P is equal to 0, then we need to have the Gaussian less than or equal to 4. It's necessary. If P is equal to 1, then the Gaussian needs to be less than or equal to 3, because we care about their sum being less than or equal to 4. If P equals to 2, we need the Gaussian less than or equal to 2, and so on, basically. Great. These are all the situations in which the sum is less than or equal to 4. So we can write it like this. Probability that B less than or equal to 4 is equal to probability that P equals to 0 multiplied by the probability that G less than or equal to 4. This is basically the first case here. Then, if P is equal to 1, then G needs to be less than or equal to 3. That's going to be the second case here that we discussed. And so on. If P is equal to 2, then we need G less than or equal to 2. If P is equal to 3, then we need G less than or equal to 1. In general, we can write this as in a nice way. We can write this as the sum, where we're counting over the values of the Poisson, basically. When the Poisson is equal to I, necessarily we need G less than or equal to 4 minus I. So we can write this concisely like this. Okay. We can even write it in an even more concise way. We can say the probability that this Poisson 2 is equal to I, let's just call it P of I. So it's P of I times the probability that G less than or equal to 4 minus I. We have this as a sum. So that's the very nice thing about the Poisson. It takes exact values, and based on them, we can see what the Gaussian needs to be such that the sum is less than or equal to 4. Okay, but now still we have an issue with evaluating these probabilities, right, of the Gaussian being less than or equal to the value that we need. So I'm going to make an observation. It's something that I mentioned in the preliminaries. The fact that G has the same distribution as a Gaussian with mean 2 and random and variance 2 means that we can write G as 2 plus epsilon times square root of 2, where epsilon is simply a normal 0, 1. It's a Gaussian with mean 0 and variance 1. So our probabilities, the probabilities above, can be rewritten like this. If the Poisson is 0, then we need G less than or equal to 4. So 2 plus epsilon square root of 2 less than or equal to 4. If the Poisson is 1, we need G less than or equal to 3. So 2 plus epsilon square root of 2 less than or equal to 3. And so on, basically. What I want to do now is I want to write everything in terms of epsilon. Because we know a lot of things about the normal 0, 1. So 2 plus epsilon square root of 2 being less than or equal to 4 is the same thing as saying epsilon square root of 2 less than or equal to 2. I'm basically just moving the 2 on this side. Okay, well, let's continue. 2 plus epsilon square root of 2 less than or equal to 3 in this other case is the same thing as saying epsilon square root of 2 less than or equal to 1. Then for P2, like if the Poisson is equal to 2, then we need 2 plus epsilon square root of 2 less than or equal to 2. So that's the same thing as saying epsilon square root of 2 less than or equal to 0. Okay. Now let's write it specifically in terms of epsilon. This is P0 times the probability that epsilon less than or equal to 2 over square root of 2 plus P1, probability that epsilon is less than or equal to 1 over square root of 2 plus P2 times probability that epsilon less than or equal to 0 over square root of 2, which is just 0. And so on. And so on, let's add P3 as well. P3 times probability epsilon less than or equal to minus 1 over square root of 2. Okay. Now, the great thing is these probabilities are well known, basically. They even have a name. This is called the CDF, yeah, the cumulative distribution function. So this is the cumulative distribution function of the normal 0, 1, which we can denote by big F. So this is P0 times F of 2 over square root of 2 plus P1 times F of 1 over square root of 2 plus P2 times F of 0. F of 0 is 1/2. That's nice. What's the chance that a normal 0, 1 is less than 0? It's the same thing that we discussed a few minutes ago. The normal 0, 1, like any Gaussian, is centered around the mean. So the chance that it's less than 0 or less than or equal to 0, it's exactly 1/2. Great. Plus P3, F of minus 1 over root 2, and so on, basically. Okay, we are making a lot of progress. This is the probability that B is less than or equal to 4, okay? And now we wrote it in this form, but we also know all of these values. These are the Poisson probabilities. So we know all of these values. Moreover, we have, there are approximations of all of these values as well. So now the question is still, is this value, is this big sum, this infinite sum, is it less than 1/2 or bigger than 1/2? Now, this becomes interesting. So all of these terms, first of all of these terms are always positive, right? This is positive. Everything else, everything here is bigger than or equal to 0, right? Because like we're just multiplying two probabilities and they both are at least equal to 0. So we have an infinite sum of positive things. So we know that this sum, keeps getting bigger and bigger as we add more terms. So we want to decide or we want to figure out if this sum converges, right? Like if it goes to something bigger than 1/2 or something less than 1/2. To prove that it's something bigger than 1/2 is kind of easier, right? If we want to prove that it's bigger than 1/2, we just want to we can just say, if I add enough terms, like maybe the first 7 terms are going to be bigger than 1/2. So the whole thing is bigger than 1/2, right? Because it's the first 7 plus all the other terms. If we need to prove that it's less than 1/2, that's a bit more difficult, right? Because we need to prove that no matter how many terms we add, it's always going to be less than 1/2. Okay, so let's say we don't know the answer, right? Now we don't know the answer. We're trying to figure it out. Well, let's actually let's start to approximate these values, okay, to see what this probability looks like. So let's do it. We know that P0 is 1 over e squared. We know that P1 is 1 over e squared times 2. P2 is 1 over e squared times 4 to the 2 factorial also times 2. P3 is 1 over e squared times 2 to the 3, right? Divided by 3 factorial, which is 1 over e squared times 8 over 6, okay? Which is 1 over e squared times 4 over 3. Let's do P4 as well. P4 is 1 over e squared times 2 to the 4th over 4 factorial, 1 over e squared times 16 over 24. This is the first term that's less than 1 over e squared. So 1 over e squared times 16 over 34 is 16 over 34, it's 2 over 3. Okay, so let's approximate these values. By the way, we can also do this in a Python script. But for now, let's just stay on the whiteboard. Let's stay on the whiteboard and let's just calculate these values real quick. So first of all, let's write 1 over e squared. Let's see what that looks like approximately. 1 over e squared. Okay. Go to the whiteboard. This is, wait, 0.135. It's at least 0.135. 0.135. Well, yeah, so let's put this approximation sign, but it's at least 0.135, right? Like it's more than 0.135. Okay, then if we multiply it by 2, we get more than 0.27, right? This one is also 0.27. This one, 0.135 times 3 over 4. Okay, let's see what this is equal to. 1 over e squared times, no, sorry, times 4 over 3. Times 4 over 3 is 0.18. It's at least, like it's bigger than 0.18. 0.18, okay. And finally, P4, 1 over e squared times 2 over 3. Let's see. 2 over 3, perfect. Is this correct? Yes. This is going to be 0.09, at least 0.09, right? Excellent. So we have an approximation for the first 4 values. Okay. This means that, and actually, like all the probabilities are bigger than these values, right? We saw together when we put it in the calculator. So the probability that B is less than or equal to 4 is, instead of P1, I'm going to write 0.135 times f of 2 over square root of 2. 2 over square root of 2 is actually just square root of 2. But we're going to do that next. Plus 0.27 times f of 1 over square root of 2, okay? Plus 0.27 times f of 0, which we know is 1/2, plus 0.18 times f of minus 1 over square root of 2, plus 0.09 times f of minus 2 over square root of 2, plus some other stuff, right? Like plus all the other terms. Plus all the other terms, p of k, f of 2 minus k over square root of 2. Is this right? Yeah. Plus all the other terms, yes. P of k, okay, 4, k bigger than or equal to 5. Okay. Let's just approximate these first few terms and see what it looks like, and then see what they look like. So now we need to approximate these values. Okay, but this is not so bad because we again can just plug them into a calculator. So let's go to the shared screen, and I'm going to say normal CDF calculator. Yeah, we have many options, actually. Let's go to this link. This looks a bit... Let's find something better. Yeah, the Wolfram Alpha should be just fine. Okay, so let's do the normal CDF for 2 over square root of 2. Super. We need to calculate this probability, right? Like this is what it's asking us. Or sorry, this is what we're asking it. And this is how we can view this graphically. And we see here that the probability of getting a value less than square root of 2, which is equal to 2 over square root of 2, this is 0.92 plus some other stuff. Great. So This is at least, so now let's go here. This is at least 0.135 times 0.92. Okay, good. Let's continue. Let's see what this probability looks like. F of 1 over square root of 2. No problem. We put it here. 1 over square root of 2. Okay, this is 0.76. 0.76. Good. 0.27 times f of 0 is just 0.27 times 1/2. Okay, we know this. Then we have f of minus 1 over square root of 2. Let's see. Minus 1 over square root of 2. It's basically a lower, like it's a smaller and smaller region, so the probability is lower. This is 0.2398. So let's say 0.18 times 0.18 times 0.239. Because basically I'm always approximate, like I'm choosing the value so that this is always bigger than or equal to this. Okay, good. And finally, 0.09 times, let's calculate this final probability, minus 2 over square root of 2 is the same thing as saying minus square root of 2. We're going to see it in a second. They're going to correct it for us, basically. Minus square root of 2, 0.078, and some other stuff. So let's say 0.078. 0.078. Plus some other stuff. Okay, so the probability, and actually, yes, I wrote that it's bigger than this. This is true, but for now, let's just do an approximation, okay? Now, let's see what this looks like. Let's actually calculate these values. No problem. It's 0.135 times 0.92 plus 0.27 times 0.76 plus 0.27 times 1/2, which is 0.5. Look at this. It's getting bigger and bigger, and it's getting closer to 1/2. Maybe we're gonna go above 1/2. So 0.27 times 0.5. Then we have 0.18 times 0.239. Look at this. We've already crossed the 1/2. Let's add the fifth term, 0.09 times 0.078. Yeah, wonderful. Did we make any mistakes? 135, 27, 27. This looks fine. 92, 7605, 23. Yeah, this is good. Okay, so if we go to the whiteboard, what do we get? We get that all of these things that we approximated here are equal to 0.51, right? Let's see, 0.5144, right? So our probability is 0.5144 plus some other stuff, right? So clearly, our probability that b less than or equal to 4 is bigger than 1/2, okay? This is fantastic. We proved that the probability of b being less than or equal to 4 is bigger than 1/2. Well, here's what this means. It means that if we plot the probability distribution function of b, let's assume it's something like this. I mean, we don't need to know the exact shape. Of course, it's bigger than 0, but yeah, I'm just doing it by hand. So it means that, what does it mean? It means that 4 is, 4 4 is somewhere here Okay. 4 is somewhere here, and it covers more than 1/2, right? The probability of being less than or equal to 4 is more than 1/2. Well, this means that the number where we have exactly 1/2, the median A, has to be less than 4. So median of B is less than or is strictly less than 4. Oops. So median of B is strictly less than 4, which is the median of A. So A has the higher median. That's the answer. So this was the challenge. Okay. I hope you enjoyed it. Let me know any thoughts, any comments. Yeah, just write them down or message me. And I want to show you a quick summary of what we did. So let's go to 1 second. I want to show this to you in a Google Doc. So let's go to the monthly challenge. Let me create a new document here. Where we do a little summary. Summary of what we did today. So monthly challenge 1 summary. So first of all, we defined, okay, so actually let's write down the statement. The problem was, or the exercise was, that A is a random variable, which is a Poisson 2 plus a Gaussian 2, 2. B was a random variable, which is a Gaussian 4, 4. And the question was which of the two random variables, A or B, has the highest median. Okay, here's how we solve the problem. First, we describe, what's a random variable and what's a median, just for those who are not familiar with these concepts. Then we did the following thing. First, we actually stated it. We didn't even prove it. Like, we took it as given because it's such a standard result. Gaussian of any mu and s squared has median mu. Okay, this is because the Gaussian PDF is symmetric around the mean mu. Okay, so in particular, the Gaussian 4, 4, so B has median 4, okay? So the question remains, is the median of A bigger than 4 or lower than 4? It could also be equal to 4, but we're gonna see that it's not. How do we tackle this? We calculate probability that A. By the way, yeah, technically speaking, I think this was B and this was A, right? How I wrote it on the whiteboard, so we can do it like this properly. Yeah, so A has median 4. Is the median of A, sorry, is the median of B bigger than 4 or lower than 4? Great. To do this, we calculate the CDF, basically, of B at 4. So what's the probability that B is less or equal to 4? If this value is bigger than 1/2, then A has a higher median. And if this value is less than 1/2, then B has a higher median. And then we approximate probability that B is less than or equal to 4. This probability that B less than or equal to 4 is a sum of terms, okay? When the Poisson equals to 0, then we require the Gaussian to be less than or equal to 4, right? When the Poisson is equal to 1, we require the Gaussian to be less than or equal to 3. Gaussian be less than or equal to 3, and so on. In general, when the Poisson is equal to k, we require that the Gaussian is less than or equal to 4 minus k. Wonderful. We know all these probabilities. Now we need to approximate these probabilities. But we have another trick. The probability that this Gaussian with mean 2 and variance 2 is less than or equal to something, less than or equal to x, is equal to the probability that 2 plus square root of 2 times a normal 0, 1 is less than or equal to x, which is the probability that the normal 0, 1 is less than or equal to x minus 2 divided by square root of 2. Let's do it like this. Okay, which is just equals to f of x minus 2 divided by square root of 2, where in general, f of t is the probability that the normal 0, 1 is less than or equal to t. Okay, super. So we have great. So we have the exact values of the Poisson, and then these values we can write as a function of the normal CDF, this f of t. Great. So probability that B less than or equal to 4 is a sum of terms of the form Poisson of k times normal CDF at 2 minus k divided by square root of 2. It's a sum of all of these terms for k, like when k is 0, 1, 2, 3, and so on. Okay. And then we approximate p of 0, p of 1, all the way to p of 4. We approximate them because we know the exact value of the Poisson with lambda 2. Okay? Then we also approximate their correspondence, like these parts that we multiply. So we approximate their correspondence or their counterparts. Okay? And then we sum them up, right? We sum everything up, and we sum up the first 5 terms. So when the Poisson is 0, 1, 2, 3, 4, we sum up the 5 terms, and we get 0.5144, if I'm not mistaken. Yeah. The important thing is that this is bigger than 1/2. So basically, this sum of terms, like the first 5 terms are already bigger than 1/2. So the entire sum is going to be bigger than 1/2. So probability B less than or equal to 4 is larger than 1/2. Therefore, the median of B is less than 4. So indeed, the median of B is less than the median of A, and this was basically our plan for the problem. So at the end of the day, we had to know the Poisson PDF, we had to know how to go from a Gaussian 2 to this general normal 0, 1, okay? We had to know that we can actually find these values, or we can approximate these values. And then this interesting technique of comparing B to the median, you know? In our case, this was nice because we have an infinite sum, but it's bigger than something, right? Proving that an infinite sum is less than something is trickier, right? If you want to prove that an infinite sum of positive terms is bigger than something, we just need to find enough terms, you know? And then after that point, like if it tips over the 1/2, then we know that the whole sum is going to be bigger than 1/2. Great. Okay, so this was the problem. Some final remarks, more remarks. You could say, why did I choose these exact values for 4, 2, and 2, 2? So here's why I chose them. You can prove the following nice things. You can prove that A and B have the same mean and the same variance. So basically, A and B are similar in these two ways, but they are not similar when it comes to the median. So try to think about this exercise. It's quite nice. I mean, for A, we know everything. We know its mean and its variance. They're right here. But prove that B has mean 4 and variance 4. You can totally do it. These are I don't want to say elementary, but these are kind of simple concepts about random variables. Actually, I'm going to tell you how to do it. So the important thing is when I'm adding two random variables, always when I'm adding them, their expected value is just a sum of the expected values of each of them. And when I am adding two random variables which are independent, and now it's important that they're independent, the variance of the sum is just the sum of the variances. So I think that's a very good starting point for you to prove that B has variance of 4. Okay, what else? Yeah, let's do a shout out to a few people who thought about the problem. Let's give a shout out to Daniel, to Ben, and to Katalin. They thought about the problem, very nice. And something very cool, something very, very cool. So above, we showed that the median of Poisson 2 plus Gaussian, I'm going to write it like this. This is like a standard way of writing it. So we proved that the median of a Poisson with lambda 2 plus a Gaussian with mean 2 variance. So we prove that this median is less than 4. Okay? A more general result holds. In general, we have that the median of Poisson of 2 plus a Gaussian with mean 2 and any variance V, any variance V bigger than 0, this is also less than 4. So basically, here we proved that if my Gaussian has this particular form, with the variance of 2, then the median is less than 4. In general, if this one is a Poisson with mean 2 and any variance, then this result also holds. So basically, we have a more general result here. And the proof is super cool, super, super cool, because basically we could try to do something similar to this, but we need to be super careful, right? Because now we need to prove it for any V, So this result and the proof are super cool. And if anybody's interested, I'm very happy to post a discussion about this because it's quite a nice discussion. And yeah, we're going to be doing some quite nice things. So if you're interested, just let me know. And that's it for today. Thanks for watching, and I'll see you soon.